I'd like to introduce Professor Michael P. Brenner today. Professor Brenner is the Michael T. Cronin Professor of Applied Mathematics and Applied Physics and Professor of Physics at the John A. Paulson School of Engineering and Applied Sciences at Harvard. His research uses mathematics to examine a wide variety of problems in science and engineering, ranging from understanding the shapes of bird beaks, whale flippers, and fungal spores, to finding the principles for designing materials that can assemble themselves, and answering ordinary questions about daily life, such as why a droplet of fluid splashes when it collides with a solid surface. So without further ado, Professor Brenner, over to you.
Good. Yeah, thank you so much for having me. It would be more fun to do this in person, although I guess this is easier for everyone. So I'm going to share some slides. Let's see. Can you guys see this? Can you see my screen? Okay,
yeah.
So I'm going to tell you about a class that we developed at Harvard starting in 2010. It's still going to this day, although I retired from teaching it, about maybe 5 years after it started for reasons that will probably become apparent as I go through this. I mean, to me, this class actually is kind of typifies. It's something that, I mean, maybe you could do it someplace else, but it really, is something that I see as like, it uses all the strengths of Harvard. And so it's a bit of a whirlwind. I have way too many slides for the amount of time that we have. My hope is to give you a flavor of the class as it was invented, why it was invented, what we covered in the class, what we tried to teach the students. And then, I'm happy to take questions and talk about this more. So this is a picture that I like very much that kind of typifies what happened. So the class was called SPU 27, Science of Cooking. And so there was always when I used to teach it, it was on Tuesdays and Thursdays at 1, and it was in the Science Center in a large lecture room. And there was a physics class, Physics 15, that happened right before. And the physics class found that they had to put a sign on the door saying, please don't come in until after this class is over, because it was just kind of such a madhouse. So the science of cooking is a subject that has been studied for a long time. So to my understanding, the first book that was written is called The Physiology of Taste by Jean-Brieuc Sévérin, who published the book in the early part of the 19th century, and it was called The Physiology of Taste. And at the beginning of the Physiology of Taste, he has a set of aphorisms, basically sort of summarizing the subject. And many of them you can't actually read in polite company, but one of them I think captured very much what we were trying to do educationally with this class, which is he said that the discovery of a new dish confers more happiness on humanity than the discovery of a new star. And so this is, this class, as you'll see, was a sort of a way of teaching science to non-scientists. And of course, probably when many of you were at Harvard, the physics for poets classes tended to be about things like stars. And, we basically said that, no, we're going to make this about food. And in fact, we're going to try to discover new dishes. And so in order to do this, as I tell you, we kind of ended up working through a series of events that I will describe with some of the very best chefs in the world, and became friends with them. So this is Jose Andres, for those of you who are foodies. When we wrote our book, which was mentioned at the beginning, Jose wrote the foreword, and I mean, and it's kind of amazing. I mean, I'm still amazed that just how much passion there was from both, not only, I mean, it's easy for the scientists to be passionate, but from the chefs to make this happen. And this book has within it, recipes from the chefs, which we analyze, scientifically. And indeed, as you will see, that's how the class went. So what I want to do is the following. I think I'm probably going to spend my time just telling you background about the class, how it came to be, what the educational goals were, tell you a little bit about just the teaching part of it. If there's time, I can talk about science concepts, but probably there's not going to be time for that. And then I'm happy to take any questions. So the class started when I had a postdoc whose name was Oje Campos, who was from Barcelona, and he was doing research with me on various esoteric science topics. And one day he walked in and said, I think it would be nice if we invented Ferran Adria to come and give a talk at Harvard. And I am not a foodie, and I had no idea who Ferran Adria was. And so I said, who is Ferran Adria? And he explained it to me that he was this very famous chef, and that and I said, but why would I want him to come and give a talk? I mean, we're busy. And he said, well, you might be interested in the things that he creates. So anyway, it turned out that at Harvard, we have what we call the MERSEC. It's a Materials Research and Engineering Center. And it's essentially a funding structure that's been funded by the National Science Foundation in the US since the 1960s that funds basically interdisciplinary research. And one of the goals of the MRSEC is to do outreach to the public, trying to explain the science that we do to the general public. And so we invited Ferran. Auger wrote him a letter in Catalan saying, we have a very special lecture, would you come and give it? And it was, part of the MRSEC, basically outreach for the year. And so Ferran, to our surprise, agreed to come, and he then came and gave this lecture. The lecture was at 6:30 p.m. and it was in Jefferson 250. Some of you might recall Jefferson 250 is the physics lecture hall it's the lecture hall in the physics department. It has 250 seats. By 4:30, the room opened at 3:30. By 4:30, it was full. And we then literally had hundreds of people trying to get in that we couldn't get in. So I didn't go to the lecture because I'm busy and why do I need to go to the lecture for? And so instead I went to a faculty meeting, and I was at a time in my life that I felt very responsible. And so I went to faculty meetings, and it turned out that at that faculty meeting, this was just when the program in general education, which was the rethinking of the core curriculum, had been invented. And we were encouraged at that meeting by the leadership of the general education program to think of ways of teaching our field, but to students in a way that affected their lives. So then the next morning, I had a meeting with Ferran because I was Auger's advisor, and he walked into this office actually that I'm in right now, and he said, that was really great. I like coming and lecturing at Harvard. I'd like to come back. And somehow out of my mouth came the words, well, it's a university. So if you want to come back, the easiest way to do that is that we teach a class together. And he said, well, that would be great. I'd love to teach at Harvard. But the thing is that I'm running this restaurant. So he was still running El Bulli at the time. And if any of you know anything about El Bulli, you can imagine how the chef cannot get away for a semester. It's completely impossible. And so he said, but actually, so I said, well, the way it works is we meet twice a week. You have to show up on time at the class, and have to do it for the whole semester. That's the game that we're playing. And he was like, well, maybe I could come twice during the semester, but he said, but I have a lot of friends and maybe they would be interested. And so he then went back to Barcelona, and within a month, I had a list of commitments from 13 of the best chefs in the world to lecture in the class. So at the time, we had no class. And, I'm not a foodie. I had no idea who any of these people were, but it was easy enough to look them up and understand what they were. And so I literally took the list to the general education program. Some of you, well, hopefully you don't remember Harvard as a bureaucratic institution. That would be bad, but it is, as all institutions beyond a certain size, they become slightly bureaucratic. And, if it turns out if you want to teach a class in the new general education committee that is touted as being the thing that changes education, then, you need to come up with learning goals and a syllabus and example problems, and you need to really make an argument about why this is going to teach the students. And I was like, at the time, busy running the applied math concentration, and I had no time for that. So I gave them the list of chefs and said, listen, if you guys approve this, then we'll somehow make this work. And it must have been an interesting meeting. Somehow they approved it. And so we then started the class. Ferran held a press conference. That was his reaction. I'm lecturing at Harvard with, 12 of the other best chefs in the world. I basically flew to Barcelona to go meet the Spanish chefs to find out if they actually were going to do what we wanted. Like, I was kind of interested in, so if I tell you that we're having a lecture on emulsions and I ask you to make emulsions, will you make an emulsion? Or are you going to come up and show us something else, because that will mess up the pedagogy of the class? And I discovered that they were all ecstatic about participating in this. And the thing seemed like it was going to work. So we then shortly thereafter started this class. The way that it worked is that every week we had a world famous chef that we flew in and who would cook for the class. It was pedagogically set up to illustrate different parts of the physics of cooking. It was really focused on the physics of cooking. It was also a laboratory, and is a laboratory-based science class. So at the time when we started this, some of you, if you know Cambridge well, or the Harvard campus well, there's a building that's called the Northwest Building that was completed in 2008, and then there was a financial crisis, and so a lot of it wasn't used. And I discovered that there was a lab in the basement for undergraduates that had never been used, and I convinced the university to certify it as being food safe, so that we could therefore do labs where the students made recipes. They would make measurements on the recipes, and then they would eat their lab. And so that was the idea, and we just chased the wave, basically. The point of this, again, was it was a science class. It is a science class. Like, the idea, at least my idea, was that I want to teach people how to think like scientists. And I believe at least that it's possible to think like a scientist by doing all sorts of different things that we do in life ordinarily. And I just wanted to expose students to the idea that there is an organized system of knowledge. You can ask questions, you can do experiments to either validate or falsify your hypotheses, and then you can iterate to basically learn something. That was the point, to sort of teach this. But we kind of use these chefs and their dishes, like the one that is there, as a enticement in a way, or as examples to basically teach this. And I basically, I thought it was the greatest science class that had ever been taught. Anyway, I don't think that was true in the end, but I was completely obsessed with this, at the time. So every week we basically had, we had lots of problems. One problem was we didn't really have a book at the time. And, as you might imagine, if you're going to teach well, I actually had two problems. So one problem was my colleagues in the physics department were mad at me because they felt that I had destroyed the physics requirement. Because what I had done was I had introduced a cooking class that students could take to satisfy the physics requirement, and they were worried it wasn't going to be hard enough. So, and at the same time, so in order to satisfy that, there needed to be math in the class. Like, there's no way around it. But if you're going to teach a large class to people who from diverse backgrounds, and there's math in the class, there needs to be something that people can study from. But this had never been taught. So what we did as a sort of educational device was that every week we had what we called the equation of the week. The equation of the week was a single equation that was introduced to illustrate the scientific concept, and we would explain that, and that would be a focus. It was actually a pretty interesting way to teach a class, to just declare, like, walk in, there's one thing that's important today, here it is, and it provided an organizational schema. We also had a recipe of the week, which was the thing that students cook, which was also supposed to be connected to the theme, and we just ran with it. So these are pictures from the lab. There were plates and bowls, but there were cutting boards and thermocouples, and the students would make measurements. So okay, so now let me see. Hopefully this will play. So I basically at the time was I didn't actually think, I'm kind of naive, if I haven't demonstrated already, it will become clear. In my head, well, this isn't going to be that much work because, well, actually I was naive on several axes. First of all, I didn't think anyone would be interested in this because I'm not a foodie, so why would anyone else be? And, it was only a couple of weeks before the semester started that I thought to call up the general education program and say, maybe we should institute an enrollment cap in the class just in case. I quickly calculated how many students we could run through our lab every week, which was about 300, and we set that as the enrollment cap. The other thing is that I was teaching a math class that I usually teach at the same time, because I assumed that it wouldn't be a lot of work, and I would just, because once a week there would be a chef, right? And then I would say something and it would be fine. Anyway, so I was running on the first day of class. I left a little bit early, my math class. In the course evaluations, the students complained that I was always leaving early that semester to go hang out with fancy chefs. They weren't happy. But anyway, I went into the science center, and this was the scene that occurred. So this is the science center. This is a student took the picture of like what was happening in the science center. And in a second, you're going to see a younger version of me pushing through. It was just mob, basically. And so here's the younger version of me pushing through to get into the classroom. And then in the classroom, hopefully this will play.
Let's try to, so again, so I repeat, there are some seats. I don't know, I'm not exactly sure what you're supposed to do in a situation like this. But I just point out that there are some seats a little bit further. If some of you could move.
Anyway, so the thing was completely mobbed. I am.
Let's try to.
Here, wait, let's see. So the crimson, just to give you, I'll just show you a little bit of this, but just to give you. So this was the crimson. Actually, was so mobbed. The crimson made a movie about it. Let me just quickly show you a little bit.
I heard about this. I think even before I applied, I needed a fun gen ed.
That's the reason you applied to Harvard?
There were many other reasons.
Okay.
Because it's something different and it's something that's like common, like cooking and stuff like that. It's like something fun, but it's related to something that's usually possibly boring, like physics.
What was your first experience in the class? First experience in the class.
I came on time, like not Harvard time, like on time. And I was all the way in the back. Because the first day that I tried to go to class, I got like suffocated and trampled. So the line was ridiculous for like just shopping it.
All the way out the door, huge long line.
And it's just like a total mob outside.
And I didn't think there was any chance I was going to get in.
How hard was it to get in?
Well, I didn't get in.
Did you know anyone that got in?
made it through. They stuck it out. They sat in on physics 15 before class, and they just stayed there in the science center.
What are you looking forward to the most?
The labs, I think.
I think the fact that you can eat your lab is pretty much the coolest thing ever.
So, okay, I'm gonna stop this there. So I actually, I mean, like, so you all have to understand, I don't know what your experiences were in college. So I teach math. Like, you see my blackboard? So there are equations all over it. So, if you teach math, like, I like math, I think it's got its benefits, but like, nobody wants to come. I mean, maybe some of them do, but like most of them, if it's big, like it's not, this was completely different. The idea that you could teach a class that was a laboratory-based class and that students, what they were looking forward to was the labs to learn was just extraordinary to me. And I think that and really as a teaching device is what gave us a lot of effort. So we in the end had 700 people try to get in. I told them on the first day of class that, that the only 300 we took, so it was about 40%. I told them that the odds of getting in were higher than the then odds at getting into Harvard. So that was good. And then in the second class, we actually had Farron in the classroom. And I also pointed out that it was much higher than getting a reservation at Obuli. So, anyway, that was the kind of joke that we started with. So we had a lot of help from the class. So one of the people, I mean, if I tell you nothing else useful, if you didn't know this already, the best book that's ever been written on this subject, it's not as mathematical as what we needed for our class, is a book by Harold McGee that's called On Food and Cooking, that if you haven't read and you're interested in the scientific basis of cooking, I couldn't recommend it highly enough. So Harold, it turned out, wrote this book at Radcliffe in the Schlesinger Library, which, as some of you may know, has one of the best collections of cookbooks in the world, when he was a postdoc, basically. I think his wife was a postdoc at the time. And Harold basically was one of our mentors in the class. We got him, the chefs were fancy enough that Harold came. It also turned out that Harold's son at the time was a graduate student in the chemistry class, in the chemistry department, and he was one of our teaching fellows. So I always had a direct line to Harold when I got confused about what to do in the situations that you would imagine would come up in this thing. Like, for example, where do I take a world famous chef to eat? Like that was an issue that we had to deal with. Anyway, so this is Harold actually on this day, the second class.
I can't tell you how amazing it is to be standing here today. I'll try to explain, but it's going to be hard to explain. I wrote on food and cooking essentially in this building.
And I mean, you can see how happy Harold is. I mean, it's just like the idea, and I think this is the theme I want to say, is that one of the things that I learned from Farron and also from all of the chefs over the years is that, at some point I asked them, like, why are you guys so interested in this? Like, I mean, I'm interested in this. This is like amazing, but like, why are you? And one of the things they said, Farron said to me one day, is that, Harvard has an architecture school. There's an arts department. There's no cooking, right? And no major university has cooking as part of its curriculum. And this is our chance as the culinary community to basically come into a major university and explain what we do and why we do it. And so anyway, this was Farron on the first day. That's Farron. That's Jose Andres. And Farron's talking Catalan and Jose is actually someone else is translating. So what he's saying is we're here together on a very important day. This is the day that science and cooking have come together at a university. And it was, I mean, it's kind of amazing. I mean, it was very meaningful actually to everyone. I need to go to the next slide. Sorry. Okay. So that's that was the spirit. So then in the second week of the class, that was the next week, we started these transitions. We had an equation of the week, and somehow in a fit of fancy, I decided that whenever we told people the equations of the week, they had to clap. And then the other thing that happened spontaneously the second week was whenever someone presented an amazing dessert, you also had to clap. And let me just show you the first instances of these things.
It must be the case where motion and sticking are an exact balance. That's our equation of the week. You're all supposed to clap.
And so it's funny, actually, to this day, like we have Monday night lectures in the fall from visiting chefs, and the public audience in Cambridge, Massachusetts, whenever we put up an equation, they clap. We've kind of like trained, which as the mathematician in me loves, it's like, oh, people are clapping for equations. So, okay, here's the first dessert, which I can get this thing to advance. So this is Joan Roca. Just watch this.
The melon.
I aquesta és l'aigua, que està líquida encara,
And this is the water still in liquid state.
però quan cau sobre el baló congelat, es congela. Això ho fem a la taula, fa el cambrer a la taula.
So people are clapping. Now I'll show you Joan. And then I want to make a comment about this. So here's Joan. He's looking very proud of himself. He noticed he had all this equipment. So what's amazing about this, actually, and this is one of the things about these fancy chefs that was so good, is that, so this phenomenon, you notice what happened was that water was poured onto this substrate and it instantly solidified. It became ice. Now, you would think that physically that couldn't happen because, you know, if water is at a temperature below the freezing point of water, it should just solidify. But it turns out that in order for water, a liquid, to basically transition into a solid, there's a phenomenon that's called nucleation. There has to be some part of the liquid that basically becomes solid, and then that propagates through the entire thing. And that usually happens on impurities. So in water, like when you freeze water in your freezer, usually it's that there are impurities on the container or in the water that are actually serving as the nucleating centers for the ice to form. If you make very, very pure water, which is very hard because water is, I mean, lots of things like to be in water, like to be dissolved in water. But if you make very, very pure water, then you can do what we call supercooling. You can supercool the liquid to make it, be liquid below 0 degrees Celsius. And if you do that, if you ever pour the liquid, it will instantly solidify. And that's what Joan just described. Now, some of you were bored by what I just said. I promise you would be more bored if it weren't in the context of this recipe. Sorry, that is my point, is that, it's like all of a sudden I had 300 students who wanted to supercool water. Like they were like, we want to go home and do this, and I was like, wow, that's amazing. Like everybody wants to do this obscure technical thing that, I like, but like, this is what I do. And everybody wanted to do it. So the hilarious thing about supercooling water, it's actually very hard to supercool water because of what I said about water, just getting rid of impurities. It's much easier to supercool alcohol, like beer you can do, because it's the impurity distributions are, and so we couldn't, of course, tell the students that because they were all under 21, but some of them discovered it anyway, and they would go off and supercool alcohol. But anyway, so then a couple of years into the class, we made this into a Harvard X class. So actually, the reason we did this, there's a long story that's associated with this too. The reason that we did this is that at the time we still didn't have a mathematical textbook, and I thought that maybe we could use Harvard X as a way of just recording our content in high enough quality that we could have the students watch this technical parts, and then we could instead take class time and use it to do many more interesting things. And so that was the thing that drove us to basically building this class. It turned out not to quite work that way. If anyone is interested, I can describe you. This was a very interesting experience in online education and its use when trying to flip a classroom with Harvard undergraduates. That it was very interesting. But anyway, the thing exists, so people can watch it. And this was the beginning of edX and Harvard X. And so we would take the cameras into chefs' kitchens and record them and then comment on them. It was really fun. The class basically has, the enrollment, this was at some time a snapshot, but there have been more than 500,000 people who've taken this class, or at least enrolled in the class. So maybe just one or two more stories and then I'll open it up to questions. So at the end of the first year, and actually at the end of every year, we ended the class by, well, actually the first year we had both a final exam and we had a science fair, and we got rid of the final exam. I'm going to show you the final exam from the first year so you can get a flavor of how the science was taught that year. But the science fair, the idea was for the students to create something that was scientifically and culinarily interesting, combine the two. And we the first year, well, actually what happened the first year is that Farron, in October sort of called me up and said, I'd like you to come to El Bulli and tell me how the class is going. So I don't know if any of you are foodies. This was the year El Bulli shut. If I'm not a foodie, I basically didn't want to go, honestly, because I was busy teaching the class and I didn't have time to do this. But I was sort of arm twisted into going. So I went to El Bulli and which was itself an interesting experience. And then after we ate, a 45-course meal sitting next to a Salvador Dali original, we had a meeting with Farron, and he said, and I sort of told him about the science fair, and he said, what does the student who wins win? And I said, oh, I don't know, glory, it's just a science fair, if you win the science fair. And he said, well, the winning students shall come to El Bulli. And I said, I'm not going back to this class of undergraduates and telling them that. Oh, by the way, there's another interesting thing that you might be wondering of how we paid for any of this. Actually, we can talk about this in questions if you want. This was also, there are lots of issues basically that exist in this class that, are under the hood that if anyone's interested, you should ask. Anyway, so my colleague, Dave Waits, who was teaching the class with me, he's much more adventuresome than I was. And he was like, we are doing it. So we went back to Boston and I told this fellow on the upper right, his name is Nookie Postal. He was at the time the executive chef of the Boston Red Sox. I told him about this prize and he said, I'm going to beat that. And so he went to the Red Sox management and he negotiated that the prize of batting practice with the players, seats in the front row, dinner in the dining hall with players before the game. So that was also a prize. He tried to get them to be able to throw out the first pitch, but they wouldn't go to that. Anyway, so we ended up with all of these donated prizes from all of these places. And we then basically had this panel of judges come in to sort of help judge the science fair the first year. And, it was an extraordinary thing. I've never seen a group of undergraduates work so hard. With the teaching staff, we've never worked so hard. And the students really made remarkable things. There's a movie, which I'm not going to show you, that Harvard made. It's called The Edible Science Fair that you can see on YouTube if you want. Actually, but just to sort of show you a couple of things. So these students, we made aprons with all of our equations on them that we gave out to the students at the science fair. So Dave Chang, who sort of started Momofuku, gave the last public lecture in the class. And he had challenged the students before with the following task. He has this famous pork bushi. And so these students got a sample of Dave's pork bushi and they sequenced it using Harvard's sequencing equipment because there was a rule at the time that undergraduates could use any equipment for a class. They could just use it. So they sequenced it. And then they discovered several new microbial species, which was pretty cool. So that was a science fair project. Another science fair project, this student and her co-workers basically figured out a very simple and clever way of measuring the pH dependence of the browning of the Maillard reactions, which is an important reaction in cooking. It was very, very clever. And simple. I really like this one. These students, so at the time, Wiley Dufresne sort of would come and he owned a restaurant at the time called WD50. And it was a restaurant that was very much interested in using an enzyme called transglutaminase, which covalently cross-links amino acids to make foods that hadn't been made. And he wanted to make noodles purely out of Parmesan cheese. And he was having trouble doing it. And so the students figured out how to do it. And that was their project. So we had all kinds of things. So I'm going to end. I think I'm now at about 30 minutes. I'm going to end and just show you the exam, the final exam from the first year, and then we can discuss. So the final exam, this is an excerpt from the final exam. It was longer. So Bill Yossis, who was the White House pastry chef, who was a good friend and came for years to our class. Enrique Rivera was a great chocolatier from Barcelona. They decided to make Nestle Toll House cookies. And here's the recipe. So here's the recipe. And then question. During baking, much of the water content is lost. Hypothetically, if the interaction energy between the water molecules were 8 kilojoules per mole, what would the boiling temperature be? 2, taking into account the ingredients in the chocolate chips, calculate the energy content in joules. Number 3, in an effort to make cookies of uniform thickness, you decide to use your coffee cup to press the dough. Suppose the cup weighs 100 grams. You notice that if you shape the dough initially into a cube 3 centimeters to a side and put the cup on it, the dough compresses to 3/4 of its height. What is the elastic modulus of the dough? Number 4, given your calculation of the elastic modulus, please calculate the distance between the cross links in the gluten network. Number 5, you put the cookies on a pan and place it in the oven. Assume that the dough is a sphere of radius 3 centimeters and that it doesn't change shape while baking. What temperature does the center of the cookie reach? Number 6, after eating the cookies, you decide they would taste better as brownies, so you remake them into a pan with a different shape. Assume that heat is coming from all sides. How long should you cook this so that the temperature reaches the same target temperature, and so forth. So that was the exam. So this is actually, I think, a pretty challenging exam. The mean on it was like a 90%. I mean, the students sort of understood how to do it. We had, this sort of exam covered a list of scientific topics that corresponded to our different weeks, which really were mainly focused on the physics of cooking. We did some chemistry. We didn't dive into the biology. We sort of viewed that as not our thing, and this was enough to keep us busy. We did other things in the class that were fun, like we made, this is a sous vide cooker that's made out of a styrofoam can, a styrofoam box and a funnel, so we would cook eggs, at 64 degrees, but do it by having the students control the amount of boiling water in them. It's instead of using some fancy device that you can buy. We did just all sorts of things. This is Joanne Chang, who was a Harvard undergraduate. She was an applied math major, and she started Flour Bakery after starting. And she's basically come to the class literally since its inception every year and just given spectacular lectures. This is Jim Leahy, who from the Sullivan Street Bakery in New York, who invented no-knead bread. This was actually probably my favorite lecture. The students didn't like it, but I really liked it, in which he basically made no-knead bread, and we talked about it. This is Jose, who was always a good friend. The Voltaggio brothers, this is Tara Whitsitt, who was an expert in fermentation. Nathan Myhrvold came every year for a long time and gave spectacular lectures and so forth. And finally, these are my last slides. At some point, because of the class, through a kind of strange story, Top Chef came to Boston, the actual Top Chef, and I befriended. I ended up being a judge on Top Chef, so I befriended several of the celebrities, and I convinced them that they should come and run as the science fair one year, Top Chef at Harvard. And so we had a thing one year where we had Gail and Tom and Mei Lin, who was the winner in Series 12, and also Harold came, and we literally ran Top Chef Harvard. So we for the science fair, it was really fun. The students made recipes. Gail and Tom quizzed them on it. We they tasted it. We then, that was a younger version of me, and then we had them all in front, and they got quizzed, and we ran Top Chef. It was really quite the ride. Anyway, so I think maybe I'll stop there. Hopefully I've given you some flavor of what we tried to do and why we tried to do it, and I appreciate your attention.
Oh, Professor Brenner, thank you so much. I have instructed everyone to please put questions into the chat. And one of my colleagues will call on you. Can we perhaps stop the screen share so we can see everyone? That would be amazing. Thank you.
Did I stop it? I still haven't stopped it.
Okay. So Maria Sophia, are you good to read off some questions?
Happily, but I don't see yet any here.
Okay.
Oh, here is one from Kate. Yes. Kate, would you like to ask it yourself, or you want me to?
Sure. So when I saw you had gelation, I'm not sure if that was the right word, in one of your concepts to understand, and I presume you're talking about those funny pearls that sort of pop in your mouth, because I did go to El Bulli and I remember having those. So can you explain the science behind that?
Yeah, so this is a process called spherification that Ferran invented. Basically what you do is you take a liquid droplet and you coat it with a very thin layer of gel, as you're alluding to. And then you make it thin enough that when you eat it, you don't feel the gel, you just taste the sort of burst of flavor. So we actually did study this in the class. We made it, we had a lab where students spherify things and taste them. So the physics of this is actually very similar to the physics of cooking a steak, which is one of the things we told them. It's just that, so the way that this works is that there's a polymer that you put either in the liquid droplet or in the outside solution, and then what you do is you put calcium ions. The polymer is a charged polymer; it has a negative charge on it, and so what you then do is you take calcium ions, which are divalent, so they have two positive charges. And so you could imagine if I have two negative charges and I have one thing with two positive charges, that causes them to stick together. So the solid shell that you tasted around the outside, that is the gel. That is the result of making lots and lots of these bonds, like enough of these bonds. It's like random bonds, right? So that the thing actually sticks together. So you can imagine, we used to tell the students that, imagine that you're in a room with lots of people, and everyone has to hold hands with random people. So if the holding hands is entangled, so if everyone just holds hands in a line, then you don't have a solid, right? Because the line, everyone can move. But if it's random, then essentially everyone gets stuck. You can't move. That's a solid. So that's basically, that's what is happening in the gel. But the point is that in order to create the gel and make it very thin, then what has to happen is that the calcium ions have to actually diffuse into the gel and cause this cross-linking to happen. And so that is the process of diffusion, in which molecules move in a liquid, for example, it also underlies other processes that we studied in the class. So for example, heat transfer, like the way that heat moves in, like, I don't know, if you cook a steak, the outside becomes brown and the center is pink. So, one of the labs that we had in the class was to cook ceviche. where, this is, you take fish and you put it in lemon juice. And then what happens is that the lemon juice basically diffuses in, the ions, actually, the hydrogen ions diffuse into the fish, and they cause a phase transformation in the proteins, which if you use tuna, which is, common, then it changes color. So what you can do is you can measure, if you measure the thickness of the colored layer in the steak or in the tuna or in the spherified gel, actually, if you can measure the thickness of the layer, then what you've just done from the point of view of a physicist is you've measured the way that the molecule diffuses in the liquid. And so, and actually this, it turns out, is a fundamental measurement. And this is a good question, actually, that you asked. I'm glad you asked this, because this is one of the ways that our class, I think, was quite unusual, is that when you have a bunch of physicists teaching this, then what we ended up doing was we taught the recipe. So we explained the recipe, we made the recipe, but we used it to essentially measure the size of a calcium ion. Like, we actually turned it into and so we in our class, like, we measured the size of a calcium ion, we measured the size of a proton by cooking fish. We measured the heat diffusion constant of water. We didn't do that from cooking a steak. One of our favorite labs that's most beloved by the students is creating molten chocolate cake, which is the same phenomenon. Because, when you make molten chocolate cake, you put the cake batter into a jar, and then the heat diffuses in from the outside. And then what you have to do is stop it before the whole thing is cooked through. The same is true with the spherical balls, right? You would worry that, oh no, the calcium, if it goes all the way through, you'll feel like a gel thing in your mouth. It'll be terrible. It won't work. So you somehow have to stop it, actually, right? Which is an interesting issue with cooking steak too, or cooking anything. It's like, oh gosh, I've cooked my meal so it's perfect. And then you take it out and it keeps cooking, basically, because whatever it is. And we basically use this both as a way of explaining the way recipes work, and we used it to make fundamental measurements of atoms, really. And I guess as a educator, I mean, this is one of the things I kind of just found remarkable about this whole thing, and also really remarkable about the chefs, because, yeah, I'm really glad you asked this question. This was a really very good question, because, the thing is that they, people would criticize that, oh, these are fancy chefs, like, why are those the right, why is that the right thing to use in a science class? But you see, it's exactly right, because they simplified things to such a degree, especially Ferran, that in the end, he not only captured the essence of something that was culinarily interesting, but it was the essence of a general phenomenon in cooking that we could use to explain.
Very cool. Thank you.
Sorry, that was a longer answer than you anticipated. But
Although one question, why do you talk about a phase transition in ceviche? Because it remains solid. You're not changing phase.
The proteins are denaturing, right? So it remains, so it's okay. We have to define what we mean by phase transitions. This is another good question. I mean, actually, I'll tell you the story. So before I get to the ceviche, so on the first day of class, you remember when you saw this picture of me, the younger version of me, in front of the room, there were hot pans and things. And I was like, I have to do demonstrations to explain why cooking is strange. And so one of the demonstrations I did, which I still think is just, I mean, it's so simple, you're going to laugh at me, but it's sort of, I had two hot pans, like they were both heated up to be very hot. And I had a box of ice, of shredded ice. So I took the ice and I put it on the hot pan, and it flash sublimated. So you saw this big burst of gas come up because you not only melted the ice, but you vaporized it. I then took an egg, and the egg, of course, is a liquid. And I opened up the liquid and put it on the pan, and it formed a solid. So that's actually kind of amazing, right? Like, if you flash sublimate the solid, it becomes a gas. And if you heat up the liquid, it becomes a solid. And of course, the reason for that is because inside of eggs, there are proteins which denature and interact with each other. And that actually is exactly what's happening inside of ceviche as well. I mean, so whether you call it a phase transition or not, we called it a phase transition. It is a change in state of the material, and it's one that has measurable consequences. And that, in fact, you really need to control, like, depending on what characteristics you want the ceviche to have, or for that matter, your steak when you're cooking it, like the change in state. Both of them are solid, but they have very different physical characteristics, and that's in fact what you're trying to control. And so, I don't know, we call those phase transitions. I take the comment that might be a rather generous definition, but on the other hand, I think it's a fair definition, actually, that it's anyway. So.
All right, thank you for that. We have about 5-6 more questions. So let's go to Joseph and then to Niall.
Thank you. So my question is, if you got a chance to design a sequel to this class, a part 2, what kind of topics would you like to focus on, both out of your interest and where you've seen this class going?
Yeah, that's a good question. So one of the things that we were talking about doing when we were teaching it was to have a biology version of this very class running at the same time. Like, I mean, this, what I just described to you as was perhaps evident was, a bunch of physicists, analyzing cooking. But like, I always thought it would be interesting to also have a bunch of biologists analyzing the same cooking and to have two things running at once. So at some point when I had a lot of energy, I tried to get that up and going because we had the chefs. So we had the substrate for it. That was one thing. I mean, other than that, I mean, I must admit, I guess what you're asking is general education classes, like what would I do? So I must admit, well, you guys are all in Europe. So in Europe, universities, for the most part, don't have analogs of these classes. Like there is no notion of general education, right? The idea, at Cambridge, everyone studies their subject from the very beginning. You're not going to like this answer, but I must admit that as I age, the wisdom of that seems more and more apparent. So I actually have I stopped teaching the class I stopped teaching it in 2015. Essentially, I felt like I stopped teaching it for several reasons. The class is still going on and it's successful and everything, but I felt like I should go back to teaching math. Basically, that I was like, not doing it. There are so many amazing students at Harvard, and there are students who really you would like to inspire to go and create the next technical revolution in our, and I just felt that, like, just as in my own, that I should do that basically. And so I went back to doing that. It was also the case that this class, like the students got a lot out of it in different ways, but like, some of the students would take the class and they didn't really want to be taking the class. They took it to satisfy their requirement. And I sort of couldn't, I understood where they were coming from, but as an educator, I was like, but why, if where you're coming from is to satisfy a requirement and where I'm coming from is that I feel that my mission is to teach people, right? And to really try to find ways of educating you so that you can go out into the world and use your brain or whatever it is we're supposed to be doing. Like, it seemed like a disconnect. So I must admit that I have sort of soured on the idea. Sorry, I know that I probably shouldn't have said that, but that's the honest answer at the moment. I mean, I remain to be convinced otherwise. I think if, like, what you're asking is, are there other things that capture popular, the public's imagination that you could base a class on? I mean, sure, there always are. Like, I just go teach a class on ChatGPT. I could basically pull that off, basically, and everyone would be excited right now. Like, it's just, there's always stuff around. During the pandemic, we taught a class on, actually, I taught a class, maybe here's another answer. So during the pandemic, Harvard was shut, basically, for in the fall of 2020, the only students that were allowed on campus were freshmen. And so together with a couple of my colleagues, we taught a class that we just did because we felt we were compelled to. It was just such an educational opportunity that was called Managing the COVID Pandemic, in which we basically paired the freshmen with upperclassmen that were off campus and weren't allowed on campus. And we did things like measure the droplet distribution. We in their dorm rooms, we would basically have the students and create puffs of droplets, and then we would measure basically how quickly they ejected out of the windows by measuring the drop. Like when you sneeze, how far is it getting? And the students basically proved that dehumidifiers in the Harvard dorm rooms, were effective, and started a campaign about dehumidifiers. And they were all doing experiments together during the thing. And I just felt like that was another one where I was like, we must use the moment, as a teaching moment. That I think was more successful. It was a smaller, maybe more successful is the wrong word. It was a smaller group. And, we did all sorts of things with these kids. We like had them design masks and test masks. That was good. But we did that once during the fall of 2020. And I think I guess you could do that again, but it was kind of more prescient. I don't know. I'm always looking for opportunities to teach people, and I can't resist, but I'm confused most of the time what's the right way to do it.
Okay, great. And Niam is asking, what was the wildest recipe, and what did the chefs learn from participating to this program, and if that had affected any protocols in the restaurants?
Okay, sorry. Okay, so what is the wildest recipe? Is that the question? So, okay, let me go backwards. So protocols in restaurants, yes, the students invented recipes that were used in the restaurants. I showed you Wiley Dufresne and the Parmesan noodles. Those existed on the menu. There were other things that went on the menus in restaurants. That wasn't the goal, but that happened. Let's see, wildest recipe. So my favorite recipe was no knead bread, but that's because I'm a simple person and I liked it because of its simplicity. So no knead bread is the idea of Jim Leahy. you can just Google the recipe and you can find it, that you actually don't need to knead bread, which is amazing, right? Because every cookbook, every idea, it's like you must knead the bread to stretch out the gluten strands. And it turns out that's wrong, basically. And I'm not, I think I know why, but I'm not sure. But anyway, I just think that's fascinating, basically. So let's see. Those are two of the questions. I've now forgotten what the third one was.
And what did the chefs learn from that, from participating in the
Oh,
program?
the students? I mean, my goal for them.
Because for the students, if there was any in the interaction with the chefs, if the chefs also thought, and if they understood, and actually there's another question that I can combine from another in the house that says, let me find it. Well, if the chefs also understood the chemistry or the physics, the science behind it, or it was just a culinary experience for them.
Okay, good. This is a good question. So I'll tell you what I thought, and then I'll tell you what I think came across to the students. Actually, the students all have different backgrounds. So I was quite surprised, honestly. And I think the chefs were also surprised at how culturally similar people like me and people like them were. I mean, and I mean, just as the way I understood it is, I'll just tell you a story. So the last lecture that I gave of the first year of the class was called The Importance of Failure. I basically got up and said, look, you're all trying to make recipes right now that win the science fair because you all want to go to Abuli or whatever, right? And so and nothing's working, basically. I was like, I know you have these grand plans and you've planned it all out and it's not working. And so you're all sad. And then I said, welcome to my life, basically. I mean, essentially, I get up in the morning and I'm like, what can I do to scientifically, I'm trying to be a scientist here. Like, what do I do? And, if I try things that work, then I'm not doing my job, basically, because, I know how to do what works. It's known how to do. That's useless, basically. What you have to do is try things that are going to fail, and then you have to become comfortable with the uncertainty and iterating. And then often what happens, if you're a scientist, is that what you tried to do failed. So then what you do is you change the question, right? You're saying, oh, well, I thought I was going to do this, but I didn't. But if I were only trying to do this other thing, then I can declare this success. And most of the scientific things I've done in my life are all that character. I didn't mean to, but it just turned out that way if you looked at it from a different way. So then that night, it was the last lecture of the class. Then Dave Chang came from Amafuku and gave the last public lecture of the class. And his lecture, I didn't know this in advance, was called The Importance of Failure. He gave basically the same lecture. And he said that, I go in and we try to create new things and nothing works, and that we try to make the best of it. And in fact, his pork bushi was an example, which he became famous for. He was like, I just threw some pork in a thing of rice and I let it sit. I forgot that it was there. And then I'm nuts and I came back and tasted it and it tasted really good. So now I serve it, in my restaurant kind of thing, after determining that it was safe. And it was a very similar culture, basically. And I at least found that I resonated with a lot of the chefs for that reason, that we were doing very different things, but that what we were trying to do, because we were trying to be creative, that there was something, and nothing ever works, there's something about the way that we worked that was very similar. And I think that's part of the reason that the thing worked. In terms of the question of did the chefs know the science? So I guess what I would say is the chefs knew more about the materials that they were working with than any of us ever would. They wouldn't explain it the same way. I had pictures of, we would oftentimes, every year when we did emulsions week, we would have the chefs make an emulsion, and then, an emulsion, you end up with bubbles basically in the meringue or whatever it is you're making. And we, of course, would take a sample of the emulsion and put it under the microscope and show the students that there were bubbles. And I have pictures of famous chefs taking pictures on their iPhone of the screen of the bubbles in their emulsion, because they had no idea that that's what they did. On the other hand, they absolutely knew everything about it. They knew how to make bubbles. They knew how to control the bubbles. They were absolute masters of the material, and they would make things, some of their recipes were just scientifically spectacular, basically, when you thought about what they did. And I mean, just to give you an example of this, so one of my favorite recipes from the class was something that Heston Blumenthal, who's in England, actually, so this is created. He created a dish called hot and cold tea, in which what he did was he took a cup of tea and he drew a vertical line and he made half of it hot and half of it cold. And his idea was that you would pour it on your tongue and that your tongue would feel hot and cold at the same time. So, okay, if you think about this from a point of view of physics, like that's impossible, right? Because if you put half of it, if it's vertical, like they will mix basically. So, okay, so that means they can't be liquids, they have to be solids. But if they're going to be solids, they have to break when you pour it. So they have to have a low yield stress. And, if they have a low yield stress, then that means they're solid. So that means when you pour it, you're going to feel something on your tongue that is elastic. So then there's a problem that if you find a gel which breaks very easily, so that when you pour it, it will break, it still has a yield stress. And then there's this annoying fact of physics that the yield stress of the elastic modulus of a gel depends on temperature. So the hot one will feel differently than the cold one in your mouth. And then when you taste it, it's just not going to work. And so, if you ask somebody like me, a physicist, like, what else can I do to a gel to change its elastic modulus other than temperature? The other thing you can do is modulate pH. That's the only other thing you can do. I mean, it's known. It's kind of well known to all who know it well. And indeed, in Heston's recipe, that's what he did. He modulated pH with temperature to get it so that the thing worked, and that was his recipe. And on one hand, you'd think that, and actually in the recipe book, he has a page where he describes how he discovered it. And he didn't say what I just said. I'm trying to match the elastic modulus of two things that are hot and cold, so I needed to find an acid that didn't taste well that would essentially do this for me. But that's exactly what he did. And he knew it, he got it to work, he had the intuition that it would work. And so I wouldn't, but it was just different, so.
And Vicky, would you like to ask your question?
Hi, sorry for the delay. Yeah, Professor Brenner, thank you so much. I just want to know how taste fits into the picture. It's essentially a physics class, not so much, chemistry or biology. So I would imagine that, physics probably describes qualities like texture, temperature, mouthfeel, presentation, physical state, everything that you've said, but doesn't really address the issue of taste.
Yeah, that's a good question. So, I mean, taste is both the taste receptors on your tongue, and there are also, of course, the odor receptors, basically primarily in your nose. We would talk about this to some extent. We didn't go into the biology of taste. Honestly, if we had, I'm not sure how much would have been exposed. Harold McGee actually wrote a book on taste, and he would talk about taste, actually. So Harold would come and do this whenever he came and talked. The one way, though, that taste really came into our class, and this was like the physics slice of where you have to worry about taste, is that, the way that, so taste comes from small volatile molecules, basically. That's where taste comes from, because it's mainly smell. And so the question is, where do the molecules that you taste come from? And oftentimes they come from chemical reactions that happen in the food, the most important of which are caramelization and the Maillard reactions, which both occur at temperatures above 120 degrees Celsius, which is important because it's above the boiling point of water. And so what that means is that if you cook a steak, like if you boil a steak, it won't taste very good. You have to sear the outside. And that essentially introduces a severe issue into the cooking of steaks and other foods where browning has to occur, because if you overcook it basically by producing the flavor molecules. And so there's a tension from the physical process side of the constraint on what is needed to produce flavor versus what you want to do if you're trying to match texture, which is more the physics. And we would spend some time on that. So that's what we did. I'm sure there's much more that could be done, but that was what we did. So.
And the follow-up question actually on this is from what the students have created and the recipes that they came up with, what has been the most surprising element? The science, the taste, or the combination of ingredients?
I mean, to me, I was just always amazed with what they came up with. I'm not sure that I can tell you some of the things. I mean, they discovered things about what I enjoyed, myself, was just watching the students discover things. And they weren't necessarily novel things, like, and sometimes we would get in trouble for that. Like one year I was telling the students that if you're trying to bake, then you of course need to inject carbon dioxide bubbles. You need to inject bubbles into the cake because otherwise it won't rise. And of course, the reason that you put baking soda in cake is because the reactions that occur basically produce carbon dioxide during baking, which helps the case rise. And I was sort of making some offhand comment that, well, you could just inject the carbon dioxide in and forget the chemical reactions, and maybe that would work. And so one of the students inspired by this made what they called cake in a can. So they took a aerosol can and they put cake batter in it. And they then literally pumped the carbon dioxide into the batter, and they then would microwave the cake, because now they didn't have to wait for the reactions to occur. It would just, it was already puffy basically. And they were all excited about it, and thought that they had discovered it. But then it turned out that Ferrand had already discovered it and, had commercialized it. And so the students were sad. So, but I was just myself, I was like, wow, that's so great. The kids are using their brains. So like, I just really like the, watching people be inventive. And this happened constantly. I mean, like from recipes that were fancy, the example I showed you of the students who found a nice way of measuring the Maillard reactions. Like I love that. I loved all of the discoveries, like of people, just thinking, how can I measure something? And to me, that was really the point. I mean, this was not about, advancing culinary art. It was really about creating an environment where the students would learn. So.
Well, Professor Brenner, that's just about an hour, but thank you so much. I found that absolutely fascinating. Judging from the comments I've seen, I think everyone else did too. So we really appreciate you taking the time to give us that lecture today. And to everyone, thanks very much for participating and for all your great questions. This has been recorded, so I'm going to end the recording in a second. I'll send around, I've shared a few links of the various things that have been discussed today, various books, videos and the like, so I'll send that around to everyone afterwards as well too. So thank you so much.
Thanks everyone for participating. That was fun.
Thank you.
Thank you.
Thank
Many thanks.